Hi, welcome back to our lecture on practical guide to quantitative finance interviews. This is going to be our sixth lecture. And today we are going to be talking about ordinary differential equations, which is 常微分方程. So today we are going to talk about all four typical differential equation patterns that are commonly seen in interviews. So the first one, and also the most simple one, is the separable differential equations. So a separable differential equation has the form of the derivative of y on x is going to equal to some function of x multiplied by another function of y. Since it is separable, we can express the original equation as two parts, where all the elements on the left-hand side is going to be related with y, while all the elements on the right-hand side is going to be related with x. And then we can integrate in both sides to have the solution, where the general format is like this. So let's see a simple example. For example, for this question, we are going to solve ordinary differential equation, y's first order derivative plus 6 multiplied by x multiplied by y equal to 0. So why we also have a y0 equal to 1 here is to help us to confirm the constant item while after the integration, okay? So let's start. First, we rewrite the equation as this. And then we separate the left-hand side and also the right-hand side, where we can actually have dy over y is going to be equal to negative 6x multiplied by dx. And then we take the integration. So basically we integrate 1 over y dy equal to integrate negative 6x dx. Since there is no information about the range of y and x, we just think it is from negative infinity all the way to infinity. So this part is going to be lowering y, right? And this part is going to be what? It's going to be negative 3x to the power of 2. And then we do not forget the constant c. So by taking the exponential, we can have that y is going to equal to e lowering y equal to e negative 3x squared multiplied by c. And then we put y0 equals to 1 into that. So 1 is going to be EC. So C equals to 0. And y is going to be e negative 3x squared. Okay, so this is the final result. You can see basically we first write it as the standard format, and then we rearrange it to put all y on one side while all x on the other side. And then we take the integration. And if we have more information, we cancel out the constant c by putting a real value into this function. So basically, this is the full standard process to solve ordinary differential equations, especially for separable ones. Now let's go to a harder one, which we are going to use the method of changing denotations. So, okay, so what is going to happen if we just trying to write it and trying to rearrange it? We can see that it's hard to put x and y on one side and the other. Why it is the case? Because it's hard to separate this part, right? And how can we deal with that? The thing is that we don't have to force this to be y while this is x. We can change the element. So one of the things is that we can define x plus y is equal to some z, okay? And then y is going to be z minus x. So the left-hand side becomes dz minus x dx, right? Which is gonna to be dz dx minus 1. Because dx dx is canceled out, okay? And on the right-hand side, it's going to be z, and it is x minus z minus x, which is going to be 2x minus z over z. Okay, now we can rearrange it. We can have z dz 2z here equals to what? Equals to 2x okay, so sorry, wait a minute. So we can have there is a -1, so we can further separate it into 2x over z minus 1, right? So both -1 is canceled out. So we can have z dz is going to be equal to 2x dx. And then we take the integration. And then we are going to have z squared over 2 equals to x squared. Okay, plus c. So we can have x plus y squared equals to 2x squared plus some constant c. And then if we further deal with that, we have what? X squared plus 2xy plus y squared is gonna to be equal to 2x squared plus c, right? And we simplify it a little bit. X squared minus 2xy minus y squared minus c plus c is going to be 0. And this is the final result. Okay, so in the case that we cannot easily separate x and y, we can use changing denotations method to convert it into a new x and y, or in this case, x and z, to help us to convert it into a separable differential equation. And this is the first type. Now let's go a little bit deeper. The second type is called the first order linear differential equations. So there are two important things. First one, it is still first order, and basically that is why it is still linear. Because if we are related with quadratics, then we may have the second order derivative, okay? So the format is still like that. Basically, we can see what's the difference from here to here. So this time we have a function of x. We also have y, but we have like two functions of x, okay? And so the standard approach to solving this kind of equation is trying to convert it back to go back into a separable differential equation. And how can we do that? Let's go through this. We can have some kind of suitable function ix, which is called the integrating factor. So once we have this integrating factor, we can multiply the original equation with this integrating factor. And this factor must satisfy that once it is multiplied into this equation, the left-hand side will be rewritten as some kind of a new function ixy. If we call it some kind of, let's say, hxy. So it needs to be combined as the first derivative of this hxy. And then in this case, we can see what is going to happen. This one is going to become a new separable differential equation, right? We can deal with it similarly with any things we have seen before. So, and usually the integrating factor must satisfy this one. Because once we multiply the ix, you can see from here, right? This ixy first derivative multiplied by plus ix multiplied by pxy. If we satisfy this, then can be regarded as the first order derivative of ix, the integrating factor, multiplied by 1, is first order. Okay. By the multiplication rule we introduced before. And the general solution is that we just put the px, okay, upon this exponential parts power. And let's give it a try. So now we have like dy over dx plus what? y multiplied by 1 over x. We try to write it separately, and it is going to be equal to 1 over x squared. And we can find what? This is going to be the px here, right? So px equal to 1 over x. And qx is going to be 1 over x squared. And by the general rule, we can use ix, which is equal to e, the integration of 1 over x dx, which is gonna to be e log in x, right? We don't need to consider the constant I can see here. We don't need to consider it. Why it is the case? Because we only need to find one useful integrating factor. So you can use like +1, +2, any constant item. But the most convenient one is what? Is without this, we think it as 0, okay? So the integrating factor we're going to use here is just x. And then what is going to happen? We can find that actually the left-hand side part, if we multiply by x, is going to be x y slash plus y equal to 1 over x. And this part is going to be x y slash equal to 1 over x, right? And then we can take the integration. So taking out both one, and this is going to be, we need to write this as a z because this here is going to be this dz, okay? dxy, and this is dx. And this part is going to be xy, right? You just convert it back to its original format because this is the first derivative. So it's like from the PDF fx to fx. And then what we're going to have next is on the right-hand side, this is going to be, oh, sorry. Oops, this is going, let's move it up handward. So this is going to be log in x. And this time we need the c, we need the constant c, okay? Because what it has provided us with this to let us locate the real c here. And then we can have y is gonna to be x over log in x plus c, and we put y1 equals to 1 into that. We can have it is going to c equals to 1, and this is log in x plus 1. Okay, we solved this question. And this is the first order linear differential equation. Still quite simple. You just remember in the first final integrating factor, which can be easily defined by the general formula. It is e to the power of the integration of the function px dx. Okay. And the second type second typical differential equation is the homogeneous linear equations. So anytime when you see homogeneous, you know that there is something about convergence or something that they share something with similar. So it has a function like ax multiplied by a quadratic second order derivative plus a bx, which we are going to see it as the parameter, and multiplied by the first order derivative plus the cx multiplied by y. And this is going to be equal to 0, right? And then, sorry, oops. It's easy to show that if we can find two solutions to this homogeneous linear equation, and then any linear combination, okay? So this basically means any linear combination. Will be a solution to the homogeneous linear equation as well. So this is going to have a closed form solution. How can we solve that? We just need to find a characteristic equation, okay? In Chinese, we call it 特征根方程. So that's R1 and R2 be the roots of this characteristic equation. A, R2 AR squared plus BR plus C equal to 0. So there are three cases. If they are real and they are not the same, then the case is going to be like y equal to C1 multiplied by e to the power of R1x plus C2 multiplied by e to the power of R2x. And if they are the same, then this basically equal to what? C1 plus C2 ERX. Oh, sorry. So we cannot say this because actually there is an extra x here. And you can actually prove this. And if they are complex numbers, the general solution is this formula here. It seems a little bit strange why it becomes related with the trigonometry functions. So the reason is because the Euler's rule we introduced the last time, Euler's rule. Okay. Okay, so we can see this fund is related with what? Trigonometric functions, right? We have cosine and sine. This is because the Euler's rule. And let me help you to derive that. So because it has the format a plus ib and a minus ib, so we can have y equal to c1 e a plus ib x plus c2 e to the power of a minus ib x, right? And then by the characteristic of exponential functions, we can separate them into c1 eax, right? We both have eax here. So this is going to be c1 ei beta x plus c2 e negative I beta x, right? And then by the Euler's formula, ei beta x, if we consider this as theta, is going to be cosine beta x plus I sine beta x, right? And ei negative beta x is going to be cosine beta x as well, because negative, the cosine of a negative element with its positive element is going to be the same. And negative I sine beta x, right? So then we can further put these two things together. Okay. So we still have the items here. But you may ask me the question that, hey, Alan, you see that if we multiply by C1 here and C2 here, it's not going to be same with this one. So how it is the case? So still remember, let's define this as, let's first define this y1t, okay? Is going to be this one. So this is y1t, okay? And this is y2t, okay? And then we know that any linear combination, right? We can derive from here, any linear combination of these two, y1x plus y2x, right? So, oh, sorry, we should use x here. So any combination of these two is still going to be a solution. So what are we going to find? So the combination y1x plus y2x divided by 2 is going to be cosine beta x. While if we have like y1x minus y2x divided by 2, this is going to be I sine beta x, right? And this time we applied a new C1 slash C2 slash before then And this is going to be same with this one, right? Because we can just use this combination. For example, this C2 would be like a C2 slash multiplied by 1 over I. It's still okay. So we can write it into this format because it doesn't matter for the parameter before it, okay? So it doesn't matter about the parameter. You can see if this is I here and we have C1, C2, it can be generalized into this case because C1, C2 can be any constant and it could include some complex items or complex part in that. So let's now see a real question about this homogeneous linear equation. So what's the solution of this one? First, we need to find the characteristic equation. We can have like this is going to be x squared plus x plus 1 equal to 0. This is going to be its characteristic equation. And then b squared minus 4ac is going to be 1 minus 4 equals to -3. So it is related with complex number. And then we can have the root is going to be 2a negative b plus or negative the square root of b squared minus 4ac. And this is going to be 2 negative 1 plus or minus I square root 3. Okay. And then according to the formula and the general solution we just proved, this is going to be, we have like alpha here is going to be -1/2, right? And the beta here is going to be square root 3/2. So the general solution y equal to e -1/2x multiplied by c1 cosine square root 3/2x plus c2 multiplied by sine square root 3/2 multiplied by x. Okay, we finished that. So you can see as long as you remember the general solution, it becomes quite easy. You just need to solve a quadratic equation, okay? And now let's consider non-homogeneous linear equations. It's basically the same. We just replace the 0 on the right-hand side with some kind of function of x. Let's call it dx. The problem is that it has no closed form solution, but we can find that if we have a general solution for the 0 cases, right? So we can see here, if ygx is a general solution of the homogeneous with 0, then we just add one ypx to that. If ypx could solve this dx, which means when we put ypx into that, this function is going to be equal to dx, right? And then we combine them together, this y is going to be a general solution. So which means we still need to solve a homogeneous linear equation to solve a non-homogeneous one. But in addition to that, we also need to find one particular solution. By any method you could imagine, you can guess, you can do a meditation for yourself, you can pray to your God, as long as you can find one, it's okay. So let's see the case here. So for example, let's first see the first part. We are now going to solve it is equal to 1. So we just call the delta equal to the ygx. We know that it is going to be equal to this one, okay? So this is the general solution, and we let it put equal to ygx, okay? I'm not going to rewrite it here. And now we just need to find a particular solution, right? We need to find a particular solution, ypx. So you can see the result is 1, which is a constant, right? It is a constant number, which means as long as we put any variable, no matter it is first order, second order, quadratic, or linear, it cannot be equal to some kind of constant because it's not fixed. So the only thing one gets is that if we let y equal to 1, well, this then we have y equal to 1, then its first order is 0, the second order is also 0, so this matches. So the general solution is basically just ygx plus 1. Okay, yeah, quite simple. And again, for it is equal to x, we still need to guess that. So basically my responsibility here is to teach you how to guess a good solution. We can see the final result is linear, Okay, first order. So can we guess y equal to something like this? Where a is not equal to 0. Can we? No, we can't, right? Because if we put some kind of quadratic items here, then it's going to exist and being kept in y. And because this is going to be quadratic, and then y's first derivative is going to be linear, and y's second derivative is going to be a constant. And then there must be some kind of quadratic item in the final result, but we do not have any quadratic item. So our guess should be y equals to some kind of ax plus b. And then we can get a and b by reducing that. So we can have y's first order is going to be a, and y's second order is equal to be 0. So a plus ax plus b is going to be x. So a should be equal to 1. And we also have a plus b equal to 0. So b is -1. So we can have a solution ypx equal to x minus 1. Okay, and then we just put that into, just add it with cygx, we got the general solution. Okay, so this is going to be all for today's lecture. I hope you enjoy. And next time we are going to talk about linear algebra. So see you next time.